Hello, Mr. Claudia here, and today we are going to do our final lesson looking at motion and motion in a line and calculus. Today we're going to be looking at how to find the distance traveled. So this is section 9.2c. Made a little error there, but your page should be correct. Also, unfortunately, a missing space there. Hope that doesn't bug you as much as it bugs me. Okay, so Mr. Claudia is driving within the speed limit. Of course, always safely, so that he can safely arrive at school on time. He travels 40 kilometers per hour for 15 minutes. So how far has he traveled? Distance traveled. Well, okay, the total distance, I mean, even if you haven't taken physics, even if you haven't learned any formulas here, you can probably reason through this. Mr. Claudia is traveling at 40 kilometers per hour, and he's doing that for 15 minutes, which is a quarter of an hour. So I'm going to multiply this by 0.25 hours. And if I do the math, well, 40 times a quarter gives me 10. So I would guess he drives 10 kilometers. And you're correct. That is, in essence, what finding the distance is. You're multiplying the distance and the time. That's if the speed is constant. Another way we can calculate the distance is as an area under the velocity time graph. So here's my velocity time graph. So Mr. Claudia's velocity was 40, and it was 40 for 0.25 hours. So one way of finding the distance traveled would be to draw this graph and then find the area underneath it, which again is not so difficult. It would be 40 times 0.25. Easy to do if you have a constant velocity. What happens if your velocity is changing? Well, then you have to add up all the different areas, or you have to use the more advanced strategy, which is integration. Hopefully this is bringing back some memories of our integration chapter where we had to try to find the area under a curve. So what I could rewrite this as is, okay, the area under this curve is really the integral from 0 to 0.25 of this function, which is just 40 dt. So that is, okay, so what's the integral of 40? Well, what do I take the derivative of to get 40? Well, it would be 40t. Do you want to check what's the derivative of 40t? 40. Good. And now this is the fundamental theorem of calculus. If you remember, we talked about this a few sections ago. If you want to solve this definite integral, you now have to sub in the values. So I write the antiderivative with the values. Now I actually sub them in. 40 times 0.025 minus 40 times 0 gives me 40, which is just 10. So great, this was easy. This is an easy example, but this technique of using integration to find area under a curve, that is something that we're going to rely on. So just to kind of summarize, this is our last section looking at motion. So far we've learned about S at t. That's what our textbook calls displacement. I call it the position. And we have vt, which is the derivative of s at t. That's the velocity. To go from displacement to velocity, I need to differentiate or find a derivative. Similarly, if I want to go from velocity to displacement, I need to integrate. That's how I undo it. For acceleration, well, acceleration is one step further. That's the derivative of velocity or the double derivative of displacement. And this is called acceleration. This is what we looked at in our last lesson. Once again, to get from here to here, you have to differentiate. And to go back, you have to integrate. So really what we're looking at today, I mean, we spent the last few sections looking at these derivatives. Now we're going to kind of look at the integral side of things, and we're going to look at how we can integrate to go backwards. So, are we ready to do that? For the first example, the acceleration of a body traveling in a straight line is given by this function. Okay, acceleration, there we go. And then I've been given ds equals 0, okay, and I've been given and s equals 0, both when t equals 0. So I have a really unfortunate page break there, or line break. So both of these happen when t is equal to 0. So these are really boundary conditions. And okay, what are we trying to find? Find the velocity and displacement at any time t. Now there's a quick note here, especially when you think back to the rates of change lesson. What the question is asking for, it's saying find vt and at. It's not asking for a number, it's asking for an expression, so you can't use the GDC. Got a bad feeling about our space management today. Okay, so let's try doing this question. So let's go over here. If I've been given the acceleration and I want to get the velocity, I integrate. So here we go. Vt is equal to the integral of acceleration. Okay, so that would be the integral of 6t minus 2 dt. Okay, let's do that. So now we can't really hide from it. We have to remember how to integrate. So the derivative of what gives me 6t? Well, if I want to find the integral of t, I gotta go backwards. So instead of derivative, I subtract 1 from the exponent. In this case, I have to add 1, so the exponent's going to become t squared. So what do I multiply 2 by to get 6? 3. If you're not sure about this answer, you can check. What's the derivative of this? 6t. Now that's right. So essentially, when you find the integral, remember you're adding to the exponent and you're dividing the coefficient by the number that you're adding. It's kind of a circular definition. And this is minus 2t. Nice. We just did our first antiderivative in a while. So that is vt. Oh, wait a sec. This is an indefinite integral. There's no bounds here. So I'm forgetting the plus c. Now I'm sort of annoyed because this is not really a complete answer. There's a plus c there. That could be any number. Remember, the plus c exists because if you take the derivative of this, you have to get this. And the derivative of any number is going to be 0, and so this can be any number. But what number is it? Well, I have to sub in the boundary condition, which I know. So I know sub in boundary condition v at 0. Right, this was v at 0. Because derivative of position is the velocity. So velocity at 0 is 0. So v at 0 is 0. So I'm going to sub that in. So then I get 0 is equal to 3 0 squared minus 2 times 0 plus c. So I end up with c is equal to 0. Therefore, v at t is equal to 3t squared minus 2t. Okay, so let's talk about this a little bit. How is this different than the rate of change lesson? The rate of change lesson, you were given specific upper and lower limits. So you could use the fundamental theorem of calculus, you could use your calculator. You can't do that in this question. So you just have to integrate and have to write that plus c. It's not a totally complete answer. I mean, you were even given extra information in the question. So you have to sub in that boundary condition, and then you get your final answer. So be careful with that boundary condition. Frequently, these questions on an IB exam, by the time you get to the IB exam, you forget, and you just write this. Actually, you even forget the plus C. So you've done the first step, you've probably gotten a few marks, but you've missed out on the last 3 or 4 marks of this sort of question. And in fact, we're not done. We also need to find S at t, which is the integral of v at t which is the integral of 3t squared minus 2t dt. If I find that integral, it is, okay, so what can I take the derivative of? Okay, so remember, I start with t squared, I add 1, so I get 3. Then look, what's the derivative of this? 3t squared. Oh, perfect. Similar with this, I add 1, so I get t squared, and I think that works out just great. But don't forget, plus c. Next step, we sub in boundary condition s at 0 equals 0. Again, we were given that information here. S is equal to 0 when t equals 0 to 0. It's just cut off on the other side of the line. So we end up with 0 is equal to t cubed, 0 cubed minus 0 squared plus c. How nice, c is equal to 0. Therefore, s at t is equal to t cubed minus t squared. Okay, and there we have it. There's our first question. So I know it's a bit of a mess, but just beware, right? We were trying to find an expression, so we couldn't use the GDC. If you have a situation like in the rates of change questions, rate of change lesson, you might be able to use the GDC. And actually, that's what we say immediately after here. Usually, instead of finding an equation of motion using boundary conditions, you will be more interested in, or we're given questions that ask us to find the change in displacement between start and end times. So think about change in displacement. That would mean like, okay, I want to know where you are at time 2 and how is that different from how far have you traveled since time 1. And that, it looks very familiar to our rates of change lesson. This is the integral from t1 to t2 of vt dt. So we're going to see a lot of similarities in this next question to the rates of change question. A particle has velocity function via t equals 1 minus 2t as it moves in a straight line. So that's velocity. Remember, we're in the middle of this diagram now. The particle starts 2 centimeters to the right of the origin. Okay, so what does that mean? That means that that's our position or our displacement. So that's s at the start, right? Starts. So s at 0 is 2 to the right, so that's plus 2. Okay, so the particle starts at some position. Find the change in displacement between 0 and 2 seconds, or 0 and 3 seconds. So change in displacement. That is equal to, okay, well, I want to know what's the displacement at 3 seconds and find the difference between what the displacement was at 0 seconds. And the way of doing this is using integral from 0 to, what are we doing? Oh, between 0 and 3. Vt. Remember, displacement, or change in displacement, is the integral of velocity. So now I'm going to sub this in, I'm going to sub in my values, sub in my function. 1 minus 2t dt. And so now what we can do is we could punch this into our calculator and find out the change in displacement. Of course, like, this is not a difficult integral. I should be able to do this by hand. This is t minus t squared, I believe. 3, 0. Now I sub in my values, so I get 3 minus 3 squared minus 0 minus 0 squared. So that's 3 minus 9, which is minus 6. Before we go on, I will just say that this sort of question, you could have solved it this way, using the boundary condition method. So you could have found the integral and then had a plus c and then subbed in the boundary condition and then gotten an expression and then subbed in change in displacement. You could have subbed in t equals 3 and found the change in displacement that way. but it's a lot easier, as we said in the rates of change lesson, it's a lot quicker to use the fundamental theorem of calculus. So this is kind of extra information that we didn't need for this method, but it kind of helps us understand exactly what happened here. So you have to think, I can kind of do this off to the side, this isn't really necessary, but s at 3 minus s at O equals -6. So that was the change in displacement. And we know the boundary condition s at 0 is equal to 2. So essentially s at 3 minus 2 is equal to -6. Therefore, s at 3 is equal to -4. So what this essentially means is the particle starts at 2 centimeters to the right of the origin, moves how long? 6 centimeters to the left. That's the change in displacement, and then ends up 4 centimeters left of the origin. So the change in displacement, we can use the velocity information to figure it out, but it really just gives us a snapshot of where we were at the beginning and then where we were at the end, and what happened in between is kind of how we move from one to the other. Particle has a velocity function like that. As it moves in a straight line, find the distance traveled. So one thing, and this was the point of this lesson, was we were talking about distance traveled. Let's just go over the difference between these two things. So change in displacement. Change in displacement considers the direction that you've traveled. Based on a snapshot of the start and end points. So if you think about this, is what we did in the last example. We consider direction, right? Because when we looked at that last example, we were talking about directions, right? Left or right of, oops, sorry, can't see it. Left or right of the origin. And it's a snapshot of what happened in between. So we started at +2, we ended at -4. So in between, the change in displacement was 6 to the left. And so that is change in displacement. Now for this question, so there's my velocity time graph. I start at 3 and I'm moving in the negative direction. Remember, to find the change in displacement, or to find the integral, one way of looking at it is to use the integral. Another way is just to look at the area under the curve. So for this question, I've drawn the graph. Let me find the area under this curve. I'm going to add A1 and I'm going to add A2 here. So the change in displacement is s at 4 minus s at 0, which is the integral from 0 to 4 of velocity. Now again, what we can do here is find the areas instead. So I'm going to add area 1 plus area 2. So that is, okay, this area is half base times width. So half the base, well, this is 4, so this is 2. So the base is 2, the height is 3. And this area is, A2 is half, the base is 2, the height is -3. So we end up with 6, 3 plus -3, so that is 0. Does that make any sense? The change in displacement. So essentially what's happened is this object started somewhere. I don't know where it started actually in this case. It traveled in a negative direction, or no, in a positive direction, and then it traveled in a negative direction. So I can show you this using my assistant here, R2D2. So he traveled in a positive direction. So he started somewhere. Let's say he started 5 centimeters to the right of the origin. He traveled in a positive direction, Then he traveled in, for the next 2 seconds, in a negative direction. His speed is negative. He ends up exactly where he started. So in this case, the change in displacement is 0, right? Because change in displacement is based on, considers direction and is based on a snapshot of your start and end points. So he started here, he did a bunch of things, he ended there. That's change in displacement. If you were to be in a physics class, we would just call this displacement. And I always talk about Usain Bolt. You know, he runs a race, right? He runs around the track. So he starts here, and he runs all the way around the track, and he comes back, and he finishes right where he started. This is a very fast runner. What is his change in displacement? 0, because he hasn't moved at all, right? And that's what change in displacement is. Look at your start point, look at your end point. So just to kind of show you that as a little sketch. That's kind of R2-D2's motion there. So he starts at t equals 0, he starts there. At t equals 2, he's moved to the right. But then at t equals 4, he's moved back to where he started. So there's no movement. Okay, contrast that to distance traveled. Distance traveled does not consider direction. It is thinking like a car odometer that counts kilometers. So I think actually we should just note here how far did we said 3 kilometers one way, and then was it kilometers we were dealing with? 3 meters, 3 centimeters, whatever it is. 3 centimeters that way, 3 centimeters this way. Okay, so when we're talking about distance traveled, this is more kind of concept we should be comfortable with. This is actually the amount of distance you walked. So if we're talking about R2-D2 again, and we're talking about the exact same function, well, we know he traveled out and then back. His change in displacement is 0 because his difference between his start and an end point haven't changed. But his distance, well, he's logged some hours. He's logged some kilometers. He's walked 3 centimeters this way, and then he walked 3 centimeters this way. So his distance traveled is actually 6 centimeters. So that's what this question is asking you for, and that's what comes up every once in a while. So when we're talking about distance traveled, you aren't going to look at adding up a positive and a negative area. You're going to ensure that you're always adding up positive areas. So what you're going to do when we find distance traveled is you're only going to look at the positive areas. So we have this area here, and we have this area here. Distance traveled is equal to 3, well, we're going to call it A1. This was A2. This would be the absolute value of A2. So that's going to be half 2 times 3 plus half 2 times 3. So you end up with 3 plus 3, so you get 6 centimeters or whatever the guy traveled. Again, if I had to draw the picture for R2-D2, he started here at t equals 0, he drove out here, t equals 2, then he drove back here, t equals 4. I guess over here was minus 3, but here he traveled 3 centimeters, and here he traveled the absolute value of 3, which is 3 centimeters. So he traveled 6 in total, as opposed to over here, I labeled it negative 3. He did 3 centimeters this way, but then he went negative, so in total he went 0. Okay, the formula for this, distance traveled. And just for the record, in the British English and thus Canadian English, traveled has 2 L's, so you haven't made a mistake. Don't spell it the American way. The formula for this is the integral from t1 to t2 of the absolute value of vt dt. That is a formula. That's in your formula sheet. That is something that comes up very frequently. You'll be asked a distance traveled question. You don't need to do too much thinking. You just go right to this formula. It's the absolute value of velocity. And of course, you're going to use your GDC. I'll show you that in the next question. Don't even think about doing that by hand. We don't know how to do that by hand. Okay, so let's do this last question here. And actually, this is a blast from the past. This is from our first motion lesson on velocity. A particle travels in a straight line with a displacement given by this function, where t is the time and s is the displacement. Determine the total distance traveled. Okay, if you remember how we did this last time, here actually, I think I have the lesson here. When we did this last time, we had to draw a motion diagram. So we actually had to find, if you remember, we went back, we found derivatives, we found critical points. We then were able to figure out when it's moving to the right, moving to the left, and then we kind of now have a map of what R2D2 does. He goes to the right, he goes to the left, he goes to the right. And so then we just added up all of those amounts, and it was like super tedious, it took forever. But we got a distance which was 113 meters. Well, now we don't have to do this anymore. So I am going to just write it out so we can have some memories of how much work this was. But the old strategy was make a motion diagram. And it wasn't wrong, it was just time consuming. So it was a long process. We had to find the critical points. That is v at t equals 0. We had to find increasing, decreasing intervals. Find distance traveled. For each interval. And then add the totals. So we had, yeah, this kind of situation. We had to add everything up. Very tedious, took a long time, not a lot of fun. Now let's look at our new strategy. So distance traveled is equal to the integral of v at absolute value of v at t, and that's from time 0 to 7. Great. Now actually the only problem is, oh, I guess I should write it out. T1, and this is technically T2. That's the general version of the formula. Now the only problem is I don't know what Vt is, I know what St is. But luckily, I'm now an expert with motion, and Vt is the derivative of St. So that is, and this is an easy one, right? What's the derivative of St? 3t squared minus 30t plus 63. So I did that off to the side. So now I'm going to put that into my formula. So from 0 to 7, those were the time bounds, 0 to 7. The absolute value of 3t squared minus 30t plus 63 dt. Okay, now, of course, you know, we're not going to do this by hand. You don't know how to find the integral of absolute values. So we're just always going to go using GDC. Let me show you how that works. I'll probably remember. We go to our calculator mode, we press menu, everything's always in menu. We go to calculus, we go to numerical integral. Okay, this goes from 0 to 7. Now I need to put in the absolute value function. You can find this, I forget where I find, oh, control equals, and you can find the bars there. You can put the absolute value bars, or you can press the little button next to 9. If you remember that, oops, hard to see. The little button next to 9 is where you get all the weird functions. And you can scroll down and find just below on the left-hand side, the second column, or second row, you find the absolute value sign. So I now have typed that in, and now I'm going to write 3x. Remember, I always use x's. I don't use t's or other numbers. So 3x squared minus 30x plus 63, and then dx. Press enter, and there I get my final answer, 113. Which, as we said, is exactly what we did last time, but it was a lot more work. So I'm a lot happier with this fast method now. So that is our lesson on distance travel. It actually just comes down to a really straightforward formula, and it comes up almost every year. So this is an essential thing to go over. It is on your formula sheet. You should just practice with your calculator. So I think this is on all sorts of motion questions. 325, number 1 to 3, AC only, and number 4 to 5, use a GDC, please, to do those effectively. Number 6, you should be able to do without a GDC. Good luck with that, and we'll see you next time.